So as one would expect, when training starts, there's almost always this really steep decline because training improves very quickly. When's the right time to stop in this data? Yeah, well, I mean, obviously I didn't stop until 1,000 whatever's training epics, 1,000 training epics. I'm gonna say I should have stopped around 220 training epics. What do you think? Which is more important, your training accuracy or your validation set accuracy?
Oh, is it because your test goes up?
Yeah, so it depends on what your goal is. The objective of gradient descent is to always improve with respect to the data you're training on. So one would expect the training data accuracy to always forever improve, right? And in fact, it will, under certain conditions. The training data accuracy will just keep on getting better and better. But it keeps on getting better and better so slowly that eventually it's a big waste of your time as a human being to sit there and let it train any longer because, you know, it's getting better at an infinitesimal rate. So you don't want to train forever. But I'm going to claim that how well you do on the validation data is more indicative of how well your model does in the real world. Why?
Because you don't train on what you're getting.
Yeah, I mean, what's the difference between training data and test data? Training data is what it sees all the time and what the model's refining itself against. To draw an analogy, if a student goes through school and gets really darn good at taking tests, does that mean this student is really great in the workforce? Hopefully it does, otherwise what's the point of school, right? But then again, so I guess one could say this blue line is school and this red line is proficiency, right? And at first, there's a big correlation between the two. Education makes a difference in your life, right? But if you spend too long in school, is it possible you think you're getting smarter, but in fact you're not getting more effective at operating in the real world? That's certainly what happens with artificial neural networks. You can imagine that the more it sees the same training data over and over, it's going to start memorizing them, right? It's going to build into its model little structures that kind of remember those training points so that it will regurgitate them upon demand, and the training accuracy will always improve, but the test accuracy will taper off. So basically, a really good stopping criteria should be designed such that the window is not so big. Imagine the window's too big here. What's going to happen? We might test at, say, 100 epics and say, okay, we've improved. We might test at 200 epics and say, oh yeah, we've improved. We might test at 300 epics and now say it looks like it's probably time to stop because we haven't improved much. Well, maybe we have. It just happens we have. So let's suppose we go on to 400 epics and then we finally stop because our window size says to. You see that our window's kind of too big? Because if we didn't stop till 400 epics and we should have stopped at 220 epics, we're not testing at fine enough granularity to really get a good stopping criteria there. So there is a penalty for using a window size that's too big, unfortunately. What's the problem if our window size is too small?
You get stuck in
Yeah, here at about 25 epics, we say, oh, it's getting worse. Stop, quick, stop. And then, well, that would have been a really bad place to stop because we could still get quite a bit better. Yeah.
So do you do some sort of like epic saving in similar to where we like minimize the error surface or minimizing that epic surface?
Yeah, so in fact, that's a really good thing to do. And a lot of neural net implementations will do that is when you're training, every time you're going to test against your test data, if that's better than the best model you've yet seen, you'll save those weights. And then you'll train for a darn long time. In this case, it doesn't really matter if you have a good stopping criteria, because you can just train forever. And then whenever you get the best accuracy possible against your test data, you say, this is the gold standard, best weights ever, let's use this model. And as far as you know, as far as you can tell from your test data, that is the best model ever. And so this approach tends to beat other approaches for stopping. If you happen to not want to back up your weights, you just want to use the weights you get when you stopped, then it becomes more important to shrink your window down to a reasonably small size. I would recommend you do save your weights. Why? Because neural networks are very, very small models relative to other types of models. For example, decision trees, KNN models, etc., very, very big models. Neural networks, very, very, very tiny compared to other models. So on average, it doesn't waste much memory anyway. You might as well back up your neural networks at periodic intervals, pick the best one against your test data, and there's your best set of weights ever. If you really want to be sure, you can measure test data at very frequent intervals, back up your weights all the time, but you don't kill yourself doing wasteful computation. Yes?
Is there any reason why you couldn't use like a visual inspection like this for any data set?
Kind of no. So in fact, part of the reason I'm giving you assignment 3 is I want you to have some experience making a visualization just like this. And so you can, one of the hardest things for me to get students to do is to visualize their work. So, yes, I wish more people would actually build charts that show what's going on so they can look at the dumb thing and make rational decisions. So please always visualize your work. That's a good thing. Is there any reason not to? I'm sure I could come up with one. You might want it to be fully automated, right? You might not want a human in the loop, and if you want a fully automated system that's just going to take your data and train till it's done, then you need some kind of convergence detection that doesn't involve humans looking at the picture. But yeah, if your goal is best accuracy possible, having a human look at a visualization, at least it's not going to hurt you, and it will often produce very good insights. So, good thing to do. Okay, what is the gap between this blue curve and the red curve called? I will call it overfit. I'll call the distance between this blue curve and where it started good fit, or training, or positiveness, and that gap there I'm going to call badness, bad training, the kind of training we wish we didn't have. Unfortunately, it's really hard to narrow that gap. In an ideal world, the blue line and the red line would be right on top of each other, right? Because that would mean that what you measure on your training data is what you get on your test data, and as the training data improves, your test accuracy is also improving. That means that you're getting better by continuing to train. What approaches could you use? Suppose you really wanted that red line and blue line to be on top of each other, and you had power to control the problem. Okay. I'm going to claim that's a really bad solution. Here's why. No offense. Basically, that means your training data, your test data is a copy of your training data, right? In the extremum. And in that case, if you overfit your training data and then you measure on your test data and you get the same thing, you won't know how overfitted you are, right? And the whole point of having test data or validation data is so that you can know when overfit is starting to occur. So this would be an example of something that hides your overfittedness. Now that might not be how you meant to use it, but yeah. Here's a great solution. What if we add more training data? So if we had a problem that we could sample to an arbitrary extent, wouldn't you want to just sample the heck out of it? Because as soon as you had, say, infinity training examples,
you'd never be able to finish an epoch.
Yeah, you'd never be able to finish an epoch. So we'd definitely have to change the label on the horizontal axis here. That would be a worthless axis label. But kind of that's the ideal situation. A machine learner's fantasy is so much data that you can never finish an epoch. Because once you have that, then your test data becomes no different than your training data. Every new pattern you present is new, right?
And so in that case, do you see that your test data will be the same as your training data? Because you have so darn much of it, you can spare it all. What's an example of a problem where you have crazy data like that, or crazy amounts of data?
Twitter, any social media.
Sure, let's train on all the documents on the internet and teach this thing how to learn. Well, documents are being produced so fast that there will be new ones before you even reach them, right? So sure, any kind of a stream thing like that, or if you have a robot and the robot can actually generate its own training patterns by going somewhere and looking with its camera, it's quite possible to have all kinds of training sets that just provide a steady stream of data and you want to learn from them. These are really great problems because overfit doesn't become such a big problem. Okay, when you have limited training data, that usually means you're in some problem like, suppose you're trying to cure a disease. Well, you don't want to go inject Ebola into an unlimited number of people to see how they respond, so you can teach a machine learning algorithm how to recognize Ebola, right? You want to use the 5 cases that have ever occurred and train on them over and over until it learns it and can recognize Ebola or something like that. So there are a lot of cases where training data is limited and overfit becomes a huge problem. So let's learn how to analyze overfit. Okay, yes?
Wasn't there that paper we read where they modified their training patterns each time, so it's like they have infinite patterns, just as randomized in their training data?
Yes. So that's an approach called jitter. And let me just visualize the MNIST data set so I have something to look at while I do it. So here's the MNIST data set. You're all familiar with it, right? Well, these are visualizations of digits from the MNIST data set, to be complete in speaking. Turns out, while 60,000 feels like a lot of data, it does. I mean, that was painful to work with, wasn't it? A little bit? Okay, well, while it seems like a lot of data, this space of possible images is huge, right? And because it's huge, I mean, even in 28 by 28 pixel images, somewhere in there is an image of you riding a donkey while jumping from an airplane with 1,000 tons of dynamite strapped to your chest, right? I mean, that picture must be in there because you could be a picture. That would be weird. I guess it'd be in grayscale if it were in this image. You probably couldn't tell what it was in 28 by 28 pixels. But I digress. Surely you were riding a shark into a volcano because that would be the most awesome way to go ever. Point is, the space is really big. And therefore, even 60,000 data points doesn't necessarily sample this space very well. So the way they jitter the data is you take a point and you stretch it a little vertically, stretch it a little horizontally, boldify it, unboldify it. You do transformations that don't really screw up what the picture is. And do you see how that makes it? So instead of 60,000 data points, we actually have 600,000 plus data points, something like that. Usually you don't jitter and generate more data. Usually you do it on the fly, so with random parameters, then you get lots of data. Do you see how jitter could improve your model potentially? How could jitter screw up your model? Yeah, I mean, suppose your data looked like this, and the ideal model was something like that, right? And what is jittering doing? Well, you're effectively taking your data and you're putting a Gaussian point cloud around all of your points. I say Gaussian, it's not necessarily Gaussian. So assuming you're doing Gaussian jitter, right? Okay, now we have more data. What's that going to do to our model? Well, it's probably going to cause it to bend down here a little, and then more like there, and more like there, and more like there, and more like that. In this case, that could be a less generalizing model, a more overfitted model. It could be that the Gaussian points actually bleed over each other and screw things up. If you blurred it too much, I mean, you could get to the point where there were just red and blue points everywhere and you couldn't draw a line between them, right? So jitter is a technique that's going to increase your number of data points. It can, when used effectively, assuming you don't jitter too much, make it behave as if though you have more data, and that's a great solution because that helps mitigate this problem. Okay. Let's talk briefly about topologies. So let's suppose we have 3 input or 4 inputs and 2 outputs. How many hidden units do you want in your neural network? Pretend those are all the same size and this is a nicely drawn neural network. While we're at it, let's pretend I took lots of time and made a nice PowerPoint for you today. Okay. Pretend all of these nodes are fully connected such that data goes in, data comes out. You can't really control the number of inputs in your data set, right? It's fixed by virtue of the data. You can't really control the number of outputs. It's fixed by virtue of the data. You usually can control the number of units in your hidden layer. In fact, you might want 2 or 3 or 4 hidden layers. What do you suppose would happen if we remove a bunch of nodes from our hidden layer? So our neural network is just going 4 to 5 to 2. How would this model differ from one that, say, was going from 4 to 8 to 2?
Less linear.
Yeah. Yeah, remember when we were proving that neural nets are universal function approximators, and we basically said that the output layer provides a bunch of sigmoid shapes or a bunch of things that it can piecemeal together, and the output layer adds them all up to produce the final surface shape? Okay, well, if you have fewer bends to work with, you're going to make a surface that's not so bendy, right? If you have more bends to work with, you can bend it all over the place. It's kind of like, imagine a neural network is a big sheet of tin, and you're going to fit to your data by pounding on it with a mallet. Well, if you have very few hidden units, then that's a thick piece of tin, and it kind of only bends where you've hit it a lot of times. Whereas if you have lots of hidden units, it's a very, very thin, I mean, it's tinfoil, basically. And if it's tinfoil, you can crumple this thing up and bend it any way you want, and it's going to go fit to all your data points perfectly. Which one's going to achieve lower root mean squared error?